Hello, everyone. Thank you for joining today's seminar, brought to you by Amsterdam Scientific Instruments, or ASI for short. We are very excited for what's about to come and all the interesting topics we're going to discuss. But first, let me introduce our company and our guest speakers. My name is Mirto Truva from ASI, where we make fancy detectors. We configure them to meet application-specific demands, and today we will present to you Mantis³ the single-photon timepiece recam. Together with Photonis, we configure this solution for quantum science applications. To present you this new system, we have invited two scientists that have first-hand experience working with it. Dr. Andrei Nomerotski and Dr. Peter Svihra. Andrei is the deputy group leader for the Cosmology and Astrophysics group. He's involved in the Rubin Observatory operations and was part of the Brookhaven National Laboratory team. Peter is an experimental physicist with a focus on silicon pixel detectors for applications in various fields, including quantum information technologies. He's a senior fellow at CERN, and he has more than 7 years of experience with timepiece recam. Thank you both for your participation, and to our audience, enjoy.
Hello, I hope you can hear me. I will start with sharing my screen so that everyone can follow the presentation. So thank you for this opportunity that I can present the applications and utilization of the timepiece recam device. The two presentations that we prepared for you today will be split in two separate halves. I will first talk mostly about the data processing and some basically hands-on utilization of the device and the camera. And then Andrei later on will take a look at the actual quantum applications where this camera has been fully used with our small collaboration. So starting first, the generic need for having a fast time resolve cameras comes for many different light imaging applications, not just quantum information science. But these cameras are usually composed where they save data as a stream of snapshots, so that you basically have a very short acquisition window and then a longer duration while you read out the data, which is the dead time. While this is a very good approach to record nice fast movies, such as you can see here, wrap of puncturing of a small water bubble. For applications which read really order of nanoseconds timing resolution or better, this is not suitable because of the dead time that I mentioned. And for this reason, we decided to look into bringing back what high-energy physics and X-ray imaging brought to the field and apply it to photon detection science. This can benefit from achieving much better spatial resolution or equally good spatial resolution of orders of 10 of micrometers, but also achieving the temporal resolution order of 1 nanosecond or later, even better for many different applications. And the main difference is that suddenly we are not looking at the data acquisition as some integrated image, which you can see, for example, on the right, but actually looking at the photons as fully standalone objects read out in a data-driven approach. So basically reading only what we actually want to measure and ignoring whatever else is present in the data stream. But of course, using this approach, you can then still integrate back the full image, which is actually what has been done here, presented later in the paper mentioned down below. Now, how to do this? Standardly, even what I showed before with a bubble wrap, we normally use CCD or CMOS cameras, which can be intensified or not. But the idea here is to go to hybrid pixel detector technology, which has been mostly pushed through by the Medipix timepiece community, where we can have fully independent optimization of the sensor and the readout that's processing the signal. In this case, we have all of the digitization happening in each individual pixel, and you can see a zoom in on the right where these pixels are then bonded to optical sensors, which enable us to measure actual light deposition instead of high energy particles. Now, the big step and advancement that has been done by Timepics 3 chip, a quick summary, it's 256 by 256 pixels, each of them 55 by 55 micron large. In total, we achieve 14 by 14 millimeters active area. The advancements of this, which then benefit the whole approach that I described before, are in the fact that we can independently measure time of arrival and time over threshold, which represents deposited energy. But at the same time, we only read out what we actually want to measure, so we ignore any zeros, and we don't need any external triggering in which we force acquisition windows and sensitive areas. Every pixel is basically all the time sensitive in a given mode, but then it has some dead time, some order of 1 microsecond, which one needs to remember. Now, how to then take this device, this camera with a silicon sensitive sensor for photons. You can just directly take it and observe any light source. Usually in applications used phosphor 47. The modification that we had to do to achieve this in the silicon sensor was to have opening in the passivation and in the metals so that the signal can actually get through into the silicon through the layers of oxides and aluminum, but also based on different technologies in astrometry, for example, one can apply anti-reflective coating to increase the quantum efficiency of the silicon up to almost 100%. The region in green here is highlighting the phosphor 47, which is a commonly used substance in many of the light applications. But now going into actual single photon sensitivity, what we can do is place extra image intensifier in front of the device, which is then the summarized whole Mantis³ camera with a image intensifier, where we can then have single photon sensitivity based on internal multiplication, but then still recording just the flashes of light with the camera itself. On the bottom right, you can see the example of quantum efficiencies of these intensifiers and photocathodes provided by Photonis. Now, I talked about how we obtain the photons, but what does the camera actually do with them? I already hinted about time of arrival and time over threshold that we record. And simply put, you can see in the top right part of the screen that time of arrival is just time before we register any signal above a given threshold. And time over threshold just then measures the amount of signal which has been digitally shaped or analogically shaped and digitized to provide us some metric of how much energy has been deposited. In a sense of photon science, we use this as approximation of number of photons that have been recorded. And you can see on animations here comparison of what these data actually look like on the camera, where on the left you see time of arrival, color representing the different times when the actual interactions happened. And you can see a strongly resolved small clusters which represent individual flashes. But with time over threshold, we get some even more detailed information about these flashes, where we can see that usually in the center there has been more photons detected, which then correspond to bigger time over threshold value. And these two values are important because coupling them together, we can actually improve the capabilities of the device. But now, since we have a continuous data stream without any triggering, I will just very briefly hint on a difficulty that one needs to keep in mind when processing and analyzing these data. First of all, by design, the stream is not time ordered. That means that the hits that you receive from your camera can be somehow randomized in order, even if they arrived earlier or later. So first of all, we need to order them before we begin. Then we still need to select some time window just to make sure that the hits that we have, that you can see on the right part of the screen, are actually properly clustered, so that it doesn't happen to us that hits from one cluster and another are merged because they are simply not close to each other in space. Afterwards, we can perform clustering and centroiding, where we can merge these individual pixels firing together to an independent cluster. but then also we can obtain a centroid information based on the mentioned time over threshold value, which can achieve sub-pixel resolution. So better than 55 by 55 microns, we can actually get a much more precise resolution of where the center of the interaction happened. We then just need to rinse and repeat this step to continue shift the time window and continue clustering across the whole data stream that we have. Using this, we can then easily post-process very large subset of data that we have to a better situation in which then individual experiments or analysis teams can basically take over and use just the final information of maybe total energy deposited, precise information in time, and amount of and the location where the interaction actually happened. Now, going on from this, this wouldn't be enough to achieve the amazing order of 1 nanosecond timing resolution. And the problem is that each individual pixel does the shaping of the signal, but this is also by definition somehow modified so that the amount of signal reaches the same constant peaking time. And based on this, we need to perform so-called time walk correction, where based on the charge deposited, the time of arrival can be recorded at a slightly different time, as you can see on the schematic on the right. And to do this with the photon application science, ideally, we would use some triggering, some external pulses on laser or something equivalent. But in this, we can also assume that since we have flashes of light coming roughly at the same time, we can assume they are instantaneous. And so we can only, based on the clusters information, create a correction technology, correction, where we can provide this time walk correction in time based on the difference of the TOT measured. And using this, we indeed find a good correction function where you can see as a function of the time over threshold, we start with correction from something like 100 nanoseconds, and with higher energy, the correction minimizes to almost nothing. This is very important to really adapt for if the application needs better than 10 or 50 nanosecond resolution, so that it can indeed reach the final order of 1 nanosecond. And you can see in the green curve here in the same plot, that's what we actually achieved when looking at resolution of untitled photons, where we can see something like about 2 nanoseconds after correcting for this time walk effect. You can also see it, for example, on a different molecular dynamics data, where we can this way resolve 2 bromium peaks, which previously would have been fully covered on top of one another. But by applying this time walk correction, it can be then much better resolved and providing better precision to the data measured. Furthermore, since we are now running in the single photon performance and operation, we can have some metrics that help us characterize the intensifier that we place in front of the timepiece camera. You can see it here in the center as a small circle in the acceptance of the whole detector, where this is coming just from a dark rate of the camera and the intensifier placed fully in dark, where it has mostly uniform across the whole surface. But this information we can also use to look at size of the pixels in the cluster or the total energy deposited in the cluster, which can help us actually verify the efficiency, but also some gain of the intensifier that we normally use. But based on these technologies, we can also investigate effect of the afterpulsing in the intensifier itself, which is described in the bottom left picture, what it looks like. And actually looking at distance between the clusters of the pixels, both in space and in time, we can evaluate a fraction of the random coincidences that are caused by this afterpulsing. And you can see from both of these metrics, it's roughly 1.5%, which means that these are values that one needs to pay attention to and consider when actually looking into order of 1 nanosecond timing resolution, And you can see these shown as a distance between the central cluster of the pixels to the afterpulsed effect, with a small feature in the bottom right corner, which probably comes from the physical orientation of these microchannels used in the intensifiers. Following afterwards, there are many different applications that one can actually use this camera in. I will just do a brief summary, starting with molecular dynamics, where using such precise time and spatial resolution can help with understanding the momentum of the individual molecules, followed by technologies such as time projection chambers, where one can look into actual space charge distribution of the particles in a volume, where one of the axes is just translated from time into actual position during the measurement. And finally, also one can monitor lifetime imaging of phosphorescence, which can be used in biomedical studies, and this improves really a lot on the speed and amount of data taken, which the camera provides. To just very briefly summarize, before we get onto the quantum applications, in general, Timex3 camera, the Mantis³ type, is a very good addition to many different visible light detection technologies. It provides excellent resolution both in time and space, but this all is only achievable by fully understanding the data that one needs to process before fully utilizing the full power of the device itself. So I hope you take something from this presentation, that always one needs to keep in mind all of the data processing and calibrations before being able to fully utilize a device of amazing capabilities. Thank you for your attention, and I will hand over to Andrei for his part.
Hello, everybody. So I'm Andrei Nomerotski from Brookhaven National Lab, and I'll thank you very much, Peter, for the introduction of the camera and how it works, and the data post-processing. So I'll focus here more on its application in quantum information science and quantum imaging. So just to highlight again the advantages of the camera. So it's the data-driven approach, which allows to timestamp multiple photons independently. And there is no need to be synchronized for these photons, or to be coming from the pulse sources or use frames. So everything can be continuous. And that actually allows to look for coincidences in the post-processing. So below, I'll review several topics of quantum imaging, quantifying entanglement, scalability, imaging in ion traps, quantum-assisted telescopy, and then go very briefly over most recent publications and show a slide on future directions. Okay, so let's start with quantifying entanglement. One of the motivation for this is development of quantum networks. And for quantum networks, you need quantum repeaters to reproduce qubits, because simple amplification will not conserve the quantum state. So one of the techniques how to do this is proposed by Anton Zeilinger, Nobel Prize winner last year. So it's shown here. So you need to transfer a quantum state from Alice to Bob, and then you have a source of entangled states in between. Then one photon goes left, and you measure its. You do the Bell state measurement, interfering it with another photon, and after that, you know the state here. So you may need to do it several times, but at the end of the day, you will have your favorite state here, which you need to transfer, and that's how it works. And then you do it again. Now, one of the important devices to enable that is so-called SPDC sources, which stands for spontaneous parametric down conversion. So the way it works is that a photon, 405 nanometers in this case, is going, is interacting in a nonlinear crystal, and then it's split into two infrared photons, 810 nanometers. So then in our experiment, we collect these photons to fibers. I forgot to mention also that in this case, the photons are entangled, polarization entangled. So the state that comes out is HH plus VV, which means that H is the horizontal polarization and V is the vertical polarization. So then after that, after a few mirrors, the photons go to the camera. That's how we see them. Two spots here corresponding to these two photons. We register them and look for coincidences. So these curves show time difference between the photons for several values of the polarization angle, and then we start to rotate the polarizers, for both photons and record the population of those peaks. So then it's shown here as dependence on the rate or on the polarization. So to figure out the degree of entanglement, we use so-called S value. So that's a degree of correlation of photons in the beams, value a value close to 1.8 is good. So that means that the photons are polarized. Since we measure it as function of the position, we can do it actually in multiple beams and combinations between the beams, and that's shown here as a graph, 8 by 8, 9 by 9 values. Then we started to bring the cameras to different places and increasing the distance between them and measuring basically the same things. So there, one of the things that I wanted to highlight is we needed then coincidences in multiple cameras. Then the camera clock, of course, is stable only to a few ppm, which may sound great, but in fact it means that it's 1 microsecond drift per 1 second, which is of course not acceptable if you want to have a nanosecond resolution. So the cameras can be synchronized. We used a white rabbit system developed at CERN to synchronize the components of the accelerator, and that that graph shows the drift which we observed. So the scale is 1 microsecond. So then after the synchronization, we recovered the resolution to nanoseconds. Now we also use the camera for the special entanglement in the recent experiments we've done with my colleagues in Paris. So this is a preprint that we posted recently. So there we use the special correlations. So it's the same SPDC source, but now the photons, traditionally called signal and idler, they come out forming a cone, right? And signal and idler, they tend to be on the opposite sides of this cone. So this is a well-known effect, which also can be used to entangle photons. This animation show how these photons can be reconstructed pair by pair. So red dots, 2 red dots is actually 2 photons registered within a window of 20 nanosecond. So this pair, and you see that they jump around this ring, which forms a circle. Now that's in the paper. So on these graphs, you see that the photons, 2 photons populate X and Y plane, and this is plane of components of the momentum. But then if you start calculating the correlations, it's very well defined as these dots here, and they also have correlation and anti-correlation here. Okay, so moving on to quantum imaging. So one thing I wanted to illustrate here is the measurement of the Hong-Ku-Mandel effect, HOM effect. So this effect is for indistinguishable particles. If you send 2 particles to beam splitter, in fact, it's just a semiconductor, semi-transparent mirror. So there are 4 cases. So both of them can go one side, both of them can go other side, or they can pass both, or they can reflect both. So now, if particles are fully distinguishable, there's no interference between them, and the number of coincidences, on different sides of the beam splitter, doesn't depend on the arrival time difference. If the particle, however, are indistinguishable, so then these two diagrams, when particle pass through and when particle both reflect, so they interfere, and they actually cancel each other. So that means that if you look for particles coming out of from the opposite sides of the mirror, you will see nothing. If they arrive simultaneously, and this is so-called HOM dip. Now, in our setup, we use SPDC source. Say same principle as I described before. But then two photons were fiber coupled, but one of them had a adjustable distance between the couplers, the fiber couplers. So the photograph is shown here. So there is a step motor that changes the distance between these two couplers. So we can change very, very finely the delay using that. So this is an event display which shows pairs of photons coming out of a single fiber. And then we had a little defocusing lens that allowed them to be spread. Here, if we plot the coincidences of photons in two fibers as function of the delay length, we see indeed the dip here, and this it doesn't go to zero because of not perfect conditions, but we also see increase, so-called bunching of photons coming out from single fibers, as I showed here. So another thing you can do with the beams coming out from the SPDC source is spectral analysis. So there is momentum conservation and correlation, as I explained before already, but there is also energy conservation. So if one of the photons has larger energy, so the other one must have the lower energy to conserve the pump photon energy. So the two beams were sent to a diffraction grating and analyzed in the camera. So you see the raw information here. So it's two stripes, which correspond to different wavelengths of two photons. So then, if you plot one wavelength with the other wavelengths, you see very clear anti-correlation that because of the energy conservation. So that was published in these two papers here. Now, a very interesting thing could happen if you combine the HOM effect with this spectral analysis. So SPDC source, two photons go to the beam splitter to have this HOM interference, but then both photons are analyzed spectroscopically. So now actually you can choose filters during the post selection. And then, this is energy anti-correlation or wavelengths anti-correlation. And if you can choose the size of the, the range of the wavelengths which you use for the interference. And that, of course, changes the width of the HOM dip. Right? So the larger range, leads to the smaller widths. Right. So very briefly about scalability. So the camera supports up to 10 megahertz single photon rate. So single photons, not single pixel. And then, for example, you could have a grid of 10 by 10 beams, and you still can read out each of them at 100 kilohertz rate. So we implemented such scheme using the acousto-optical modulators, which created 8 by 8 grid in the camera. So one of them goes in X direction, one of them goes in Y direction. They can operate, at about 1 microsecond switching time between them. So you see here bursts of photons separated by microseconds, still providing 10 nanosecond resolution. And that's a display of 8 by 8 beam, showing TOT and TOA. And that demonstrates the flexibility. So we are planning to use it for storage of multiple qubits in single rubidium-87 cell. That's related to the quantum memory project we're doing at BNL. Okay, so now let me move to a different topic: imaging of qubits in ion crystals. So that's something we are doing with Boris Blinov group in UDAP in Seattle. They use a Paul trap to trap ions and that uses RF of 18 megahertz. Then there are ways to read out the state of this qubit, if it's dark or bright, using a laser. And in the end of the day, you then look for emission of 493 nanometer photons coming out from the ions. So that shows an image of the ions and some time dependence, which you also call telegraph mode behavior of these qubits. Now, it turns out the camera can provide very low detection error readout there. So if the rate with which the photons are coming from the ions is about kilohertz. So if you spend 5 milliseconds, so you see about 10 photons, in the case of bright state, and low number of photons for the dark state. If you wait longer, so you improve your detection error. So what we were able to achieve for the single qubit detection error is 5 ppm, which is a very good result indeed. Now, another thing that we can actually measure, and we can see with the camera, the ion oscillation. So the 18 megahertz means that the period of this oscillation is 54 nanosecond. So then what happens as the ion moves, they detune from the transition frequency due to the Doppler effect. So they emit only when they go one way, and they don't emit when they go the other way. So if you measure the rate of this oscillation, so that allows you actually to see in which phase the ion emitted. Now that shows the reconstructed movement of the ion chain. So the period is 54 nanosecond, and that was, as you see, later used to optimize the the cooling of the ions in the crystal. Now we're doing this with larger number of ions, and we also transition to the 2D crystals. So you see oscillations here of the 2D crystals of about 50 barium ions. So there the cooling is done in a more complex way, using the acousto-optical modulators to guide the beam, and also there are two beams there. And currently we are studying how the Doppler cooling can be pulsed, and this pulsing could be micromotion synchronized, because that allows you to cool very efficiently the crystal. All right, so now very briefly, let me mention another project, the so-called two-photon techniques for quantum-assisted telescopes. Well, that's something that we're developing at BNL. So the idea there is to employ quantum entanglement to improve the precision of optical interferometers. So the main idea, is coming from this PRL published 10 years ago. So the idea is that in optical interferometers, in classical optical interferometers, you need to bring light together to interfere it in one point, but that limits the distance between the stations to about 300 meters. And so the question is, can we increase this distance, and that would improve the astrometric precision of the interferometers. So the idea was to provide a source of entangled photons in between. So you interfere sky photon with entangled photon, effectively teleporting the sky photon to the other station. And that bypasses this requirement to preserve the phase for the interference, and effectively what you do, you transfer the quantum state, and then it becomes a problem, of quantum networks. So in principle, that can improve the astrometric precision by orders of magnitude. So it's two-photon interference, only indistinguishable photon interfere. So that means that you need both temporal and spectral binning with good precision to be in a single mode. So the numbers there is 10 picosecond and 0.2 nanometers for 800 nanometer wavelengths. So the target, you need very good detectors, and the target is 10 picosecond, which is of course less, better precision that Timepeaks camera would allow. So first, let me mention the spectral resolution. So we built a spectrometer similar to what I showed before, based on a diffraction grating. So you can send beams of light and beams of photon to the diffraction grating, and they're analyzed in the camera. So we send the thermal light from argon, and you see multiple lines. So we, since we can, we implemented two spectrometer. So it's a dual spectrometer then, which we later used also for the SPDC sources. But the point here is that using this, you can calibrate your spectral resolution very precisely. So that shows, for example, a doublet of argon separated by less than 1 nanometer. So we estimated our spectral resolution 0.15 nanometers. Then we also used timing from the MCP. So not timing from timepics, but timing from the MCP measured in the TDC in the timepics camera to probe how MCP timing can be used for that. We had a pulsed laser. Then one beam was delayed by 200 nanoseconds. We saw two spots in the camera. And that also 200 nanoseconds, that's enough to separate two signals coming out from the MCP and measure them in the TDC. So our resolution that we got there was of the order of 50 picosecond, which is good. Okay, so I'm running out of time. So what I'll do, I'll just flash recent publications, mostly on quantum imaging that are using the camera. So that came out in January, came out in December again, November, and a bit earlier in 21 as well. Right, and regarding the future direction, so Peter already mentioned timepics 4, and I also show probably the same information here that with timepics 4 replacing timepics 3, we hope to get the resolution of 200 picosecond. Since the camera is optical and we use a scintillate in the camera, it's not completely clear if we can take full advantage of this improved resolution. So that's the tests are in progress. Stay tuned. Okay, so let me summarize. Timestamping of optical photons with data-driven readout is attractive alternative to frame readout. It works well for sparse data, as many of the experiments are. It needs, however, intelligent pixels with complex functionality, which are implemented in timepics 3 and timepics 4. So the timing resolution of the order of nanoseconds and can be improved further with timepics 4. So then the photon sensitivity can be single photon with addition of the intensifier. And I would add that new technologies for fast signal photon detection are a hot topic in quantum application. Okay, let me end my part with this statement from Freeman Dyson, which I like very much. The great advances in science usually result from new tools rather than from new doctrines. Thank you very much. And that's my collaborators from BNL and Stony Brook.
Thank you, Peter and Andrei, for this very informative and exciting talk. If you're interested in the specifics of the Mantis3, you can visit our website on www.amsins.com for the product specifications and white papers. Connect with us via LinkedIn for more updates on products, seminars, and other events. If you have any questions on today's topic, please feel free to reach us via email at hello@amsins.com. Thanks again for your time, and we'll see you at the next one.